So today I'm going to introduce Jen. Jen Steeple joined us in 2022 as a master's student. She was doing her bachelor's in environmental science at the University of Pittsburgh, and then since joining University of Maryland, she has been working on a very important problem, very important environmental issue, not only in Maryland, but in the entire coastal plain of Mid-Atlantic, which is the groundwater decline. So she has been working on developing a model to predict the groundwater decline in southern Maryland. So let's welcome Jen.
Thank you so much for that introduction. So hi everyone, I'm really excited to talk to you today about my project, building artificial neural network models to predict groundwater levels in the Aquia Aquifer. So let's hide this. Okay. So just a quick presentation overview. I'm going to start with an introduction, and then I'm going to move into my objective 1, which is where I build, test, and train the 8 artificial neural networks, and then basically figure out how well they're working. Objective 2 is comparing them and how they do in different like moderate and high intensity climate scenarios. And then the conclusion is just a summary of what I found, and then me trying to figure out the applications for future use. So the introduction. So a little bit about groundwater in the coastal plain of Maryland. So the North Atlantic Coastal Plain Aquifer System is a 50,000 mile squared aquifer system that runs from Long Island, New York. Here, let's do the laser pointer, all the way down to the top of North Carolina. So here you see NACP, North Atlantic Coastal Plain Aquifer System. And there's about 9 confined aquifers within this aquifer system, 9 confining units, and 1 superficial aquifer. And from 1900, which is about the start of development here, up to 2008, but obviously still continuing, Maryland, Delaware, and Virginia all have had significant groundwater level declines. So this is definitely a region of concern. And let me see. There you go. So this is actually a very complicated and crazy looking map, but these are the 9 aquifers. And the one we're going to be focusing on today is the Aquia Aquifer, which is the red stripy aquifer. So Maryland's confined aquifers have experienced accelerated rates of groundwater level decline as a result of both well withdrawals and climate factors. And groundwater is the source of drinking water for about 1.4 million people on the coastal plain of Maryland, so a lot of people depend on groundwater. It's also used a lot for agricultural and industrial uses. So there's also been some pretty cool studies that have come out, and they actually found that cultivated areas on the Eastern Shore, so areas with over 50% cultivated area, had the most groundwater level declines. So maybe a little hint of agricultural withdrawals causing groundwater level decline here. And this is actually a graph of a well in Calvert County, and this is the depth to water level in feet below land surface. And as you can see, it's not looking good. So it's declining pretty significantly all the way till 2024. You see a little bit of seasonal variation there as well. So why are we studying the Aquia Aquifer? There's 7 other, or I think, yeah, like around 7 or 8 other aquifers within this system. So why is this one so important? So it's actually one of the most important groundwater resources in Maryland. It's a deep confined aquifer, and it's a significant source of drinking water for many communities, as well as an important resource, again, for agricultural and industrial purposes. And it's the primary source of groundwater in Calvert, St. Mary's, and southern Anne Arundel counties. And we actually have a number of studies done that have shown the decreases and documented the decreases in this region. There's also some issues with saltwater intrusion up in the Anne Arundel region, so there's other concerns there as well. So we want to figure out how to properly manage this aquifer in particular. So this is actually our study area. There's 8 different counties. So I will now try to list them. So Calvert, Caroline, Kent, St. Mary's, Queen Anne's, Talbot, and Anne Arundel, I think. So let's move forward. So the method I'm using, artificial neural networks. So let's talk about it. So input layer, hidden layers, output layer. And the inputs, these are all little neurons, right? So everybody has a neuron, everybody gets a weight. So essentially what the neurons are is they pass on information, and the weights decide how important the information is. So when you put in your inputs, you basically go into the neuron. Each neuron has something called an activation function. An activation function decides how that information gets passed along. It also adds a lot of nonlinearity to the model, which is really interesting and makes it very useful. And the other great thing about this approach, and the reason why I chose it, is because if you don't need to know every physical parameter of a system, this is a really great option, because you don't need to know, for example, how deep everything is, every single transmissivity of every single point, stuff like that. So this is great for that. And there's been a lot of proof that this is really great in a lot of nonlinear dynamic systems modeling. So let's go for an example that maybe will be a little bit easier to understand. So let's do price of a house. So since I am doing a regression problem, I'm predicting a range of value instead of a categorical problem where I'm picking like one thing or another, right? So our goal is to figure out the price of a house. So what are some things that we might look at if we want to figure out how much a house might be? We'll look at square footage, amount of bedrooms, bathrooms, location, and school district, for example. All these things will go in, and as you can see, they go into this black box. And that's an actual term in machine learning. The idea is, like I mentioned, there's a lot of weight adjustments happening, and the weights actually the idea is adjusting the weights to minimize something called the mean square error. The mean square error is just the difference between the predicted output and the actual output. So we're just trying to get that as small as possible. That means it would be a good model, right? So in the hidden layer, or the black box, a lot of back propagation of the weights is happening and readjustments is happening. So we can get peaks into this, but the math that's going on in here is really complex. So that's why we call it a black box, because we know our inputs, we know our outputs, and what goes on in here, it's a little bit funky, right? So so basically we put all this through, and we also, in our training, will put in how much the houses with, say, in this location are, and with this many bathrooms and bedrooms are, right? And then in the end, when we have our fully made neural network, we don't have to put in the price of the house. It'll go and tell us if we say. So if I say, okay, I've got a house with three bedrooms, and it's this big and has this many bathrooms, it'll go and look back and say, I know about houses that have 3 bedrooms and this many, bathrooms, and they're usually around this much. So then it comes up with a prediction. So let's talk about how I'm actually using it. So I'm using it to predict groundwater level. So I actually, I'll talk about my inputs more later, but I trained my artificial neural network with historical data, including groundwater levels. I also used precipitation for one of them. We found out it wasn't contributing a lot to model prediction, so I'll go into that more later. Temperature, population, and irrigated area, farm area in acres. It goes in, we get the output of groundwater level. And like I said, in training, it already knows the groundwater level, but in testing and in application, it doesn't, right? Because you're trying to get it to guess. So I have 2 main objectives, and I will go into objective 1 right now. So again, objective 1, just trying to build, train, test the neural networks. Like I said, I did 8 of them, and the reason for that is because if you look at the withdrawals within the counties, they differ a lot, and the different stressors on the groundwater differs a lot. So we want to try to get it to the smallest resolution possible for the best management. So I ended up using county level. So another important thing you need to know before we really get into the nitty-gritty is, what is NAVD88? So it's actually the North American Vertical Datum of 1988. So similar to like a latitude and longitude might tell you where things are on a map, this kind of works vertically, right? So this is mean sea level, this is NAVD88 to kind of give you an idea, great graphic by Noah. So when I talk about NAVD88 and you see a negative number, that basically just means it's under this line, right? It's under that level. If you see a positive number, it just means it's above that level. So let's get into choosing the input data. So let me break down this pretty big graphic here. I used a Pearson's correlation coefficient analysis to figure out what variables were closely linearly correlated. So these are my counties here, and then these are my variables, and I have about, I think, 41 variables. And we started with the climate variable, so Tav, Tmax, Tmin, precip. We moved to population, irrigated area in acres, and then from here on, it's actually withdraw data. So we received data on the permitted withdrawals from the Maryland Department of the Environment, and they had all these little withdrawal types already separated out, which was great. And we basically just wanted to see if any of those were connected. And where you see the blanks, it just means, for example, for aquaculture and aquarium, it just means that Talbot isn't withdrawing from the Aquia Aquifer for that use type. So when you see a red color, that is a strong positive correlation. Strong positive correlation just means those variables tend to move in the same direction. So, and then when you see a dark blue, it just is a strong negative correlation, meaning those variables tend to move in the opposite direction. So I'll give you an example. So for St. Mary's, for example, if you look right here at this negative 0.65 for average temperature, that just means when average temperature goes up, groundwater levels tend to go down. And when average temperature goes down, groundwater levels tend to go up. So this is basically how we chose our input data. So to sum things up, we looked at those correlations and we ended up picking maximum temperature, minimum temperature, average temperature, irrigated area in acres, population, and then we, like I said, we did precipitation, but I'll talk more about that later. We did it for one of the models. And then for training, we obviously needed our groundwater levels. So I split up my observed data, which is the input data, into 3 parts: training, testing, and validation. So now I'll go into what each of those steps entail. So for training, again, you see observed groundwater level data here and all of our other variables, and our goal is to get predicted groundwater levels so we can compare it to observed groundwater level to see how well the models are performing. To do that, we use something called a grid search to basically, there's some parameters that the model can't figure out on its own, and we have to give it those parameters. And the way that the grid search works is that it's a trial and error approach. So an example would be for a neural network. You know how I gave you the hidden layers and I had 3 of them? So that is one of those, we call them hyperparameters that you can adjust, and you have to adjust on your own. So you go in, you put in some numbers, you see how well it does by using the mean squared error, and you go and adjust. And we use the validation data for that. So then we know how we want our artificial neural network to be configured, and then we can actually apply it and get our predicted groundwater level and compare. So again, we want it to learn to make predictions by adjusting the weights throughout based on input data and corresponding target outputs. For testing, you can see the groundwater level is missing from the equation here because the testing is basically an assessment of how well it will do on data it's never seen before, which is why when we get to the results, I'll focus more on the performance on the testing. So that all goes in to the neural network. We get predicted groundwater level and we compare to observed groundwater level. And again, we want to minimize mean square error between predicted and observed points. So into our results, I won't show you every single county just in the interest of time, but I'll show you some representative counties. So the first thing I'll focus on is the feature importance. So for feature importance, it's basically a measure of how much a certain variable contributes to the prediction of a model. So we use a technique called permutation importance. If you do other types of modeling, you might be aware of the sensitivity analysis. And it's basically when you hold all the variables constant except for one, you change that variable randomly, and you see how much that affects model performance. So basically it says, okay, how much is this variable impacting our model predictions? And St. Mary's is an example of a model where T-min was the most important feature. And there were actually 2 other models that had T-min, or minimum temperature, as the most important feature. And if you look at the R squared for the testing set, we got 0.99, pretty good. So root mean square error basically ranges from 0 to infinity. So 0.50, pretty good score in this case. So it looks like the models are performing well. And also, so training, testing, and then this is predicted and observed. And so if it did perfectly, it would be a perfectly straight line. And I know the graphs look similar, but that's why I provided the set size, because it looks like basically these groundwater levels reach the same levels kind of over and over again. So it looks like the graphs are similar, but in fact, they are just kind of points overlapped on each other. So let's talk about Kent County now. So population was the most important feature here in the model. And R squared is again looking pretty good, 0.99. And root mean squared error was 0.21. So models are performing pretty well overall in the testing, and they're capturing the trends using these variables. Irrigated area in acres also you'll see comes up a lot as maybe the second most important feature in a lot of these models. Training is an example, or sorry, not training. Irrigated area in acres is the most important feature in Anne Arundel. Only county that had this is the most important feature. And R squared is actually 0.82, which is the lowest of our bunch, but still pretty good. Root mean squared error is pretty low, all things considered. So that's good. Let's keep going. Queen Anne's County. As you can see in Queen Anne's County, R squared is 0.98, root mean square error of 0.18, looking good, low error. And the only variable, this was crazy, that contributed positively to the model predictions was average temperature. So there are a couple reasons why this could be. One of them could be that maybe these variables would do better if they were lagged. So maybe the effects of these variables aren't affecting groundwater immediately, but perhaps there's a little bit of a lag in the effect that isn't being captured well. There's also a possibility that, that there are withdrawals that are greatly affecting this instead. And maybe some of these other factors aren't the biggest, most sensitive, to changing groundwater level out of everything. So let's get to some quick conclusions. So counties that had large amounts of agricultural area tended to have negative correlations with groundwater level. The county with the highest withdrawals, which is Queen Anne's, actually had the highest negative correlation to groundwater level out of all the counties when we talk about reported withdrawals. And the opposite was true. The county with the lowest amount of withdrawals from the Aquia Aquifer had the positive correlation to groundwater level out of all the counties. And then counties with the highest amount of irrigated farm area had irrigated farm area in acres as negatively correlated with groundwater level, and the opposite of that was also true. So Anne Arundel, the county with irrigated farm area as the variable with highest feature importance, had the lowest R squared out of all the models, and the variable with highest feature importance when the feature importance scores were all added together was irrigated area. So let's move to objective 2, where I work with the different climate scenarios. So like I said, I want to use these artificial neural networks that we just made to forecast groundwater levels under future climate and inform groundwater level management. So let's get into the climate scenarios. So this is the near future scenario, 2023 to 2050, and far future scenario, 2050 to 2100. And this is just to give you an idea of the data sets I use. So the temperature variable, for example, this is average monthly temperature, and this is the moderate scenario in the blue, and the intense/high emission scenario in the orange. And the gray is my study / base period, which was used to train and test the model. This is just to give you an idea of how these climate scenarios differ and how they might impact the model. So let's figure out how. Let's figure out how we did the methods. So precipitation temperature, population, and acres of land in irrigated farms. Put that in the neural network. Get future groundwater level. And in this case, there is no observed data to compare it to because this is the future. So something to note also real quick is that temperature is the only thing that we had the two different scenarios for. Like I said, we actually, when I talk about future importance, precipitation, we used it in one of the models. We found it wasn't really contributing much to the predictive ability of the model, so we ended up excluding it for the rest. But temperature did, and it contributed quite a lot. So we did the two different climate scenarios for these, and then population, there were actually estimates and projections up till about 2045, and then after that, we're trying to estimate up to 2100, so I had to do some linear regression and try to work that out as best as I could. And then acres of land in irrigated farms, I also kind of had to project that into the future. So here, let me get rid of this. So another thing to note is the acres of land in irrigated farms variable, and this is something that might have influenced model performance, is that this is actually all of the land in the county that is irrigated. It's not necessarily land irrigated by the Aquia Aquifer. So that's why maybe we saw that low R squared earlier, because this is the best data that is available, but ideally we would know exactly how many acres are irrigated by the Aquia Aquifer. So that is another thing to consider. But anyway, so let's get into our forecasts. I had 4 counties that we got decreasing groundwater levels for, generally speaking, trend-wise. And those were Kent, Queen Anne's, Caroline, and Calvert. The bottom here is the year, so it goes all the way from 2020 to 2100. This is a yearly average predicted water level relative to NAVD 88. And again, I had to do yearly because groundwater levels have a lot of monthly seasonal fluctuations. So the graphs would have looked really crazy if I did monthly or even deeper, like more specific scale. So I stuck with this. But the blue line is the moderate scenario, and the orange line is the high emission scenario. So we'll talk a little bit more about that. And then, surprise, surprise, I actually had counties with increasing groundwater levels, and those were Anne Arundel, Talbot, and St. Mary's and Charles. So let's figure out why that was. So that isn't expected in these regions. Obviously, we are expecting declines or at least things to stay evened out. So reasons why this could have been: variable choice. I kind of touched on this earlier, right? So the irrigated area in acres variable is just representing all the water used, groundwater used to irrigate the land in the county. Some of these counties don't actually use the Aquia Aquifer for irrigation. So in those counties, it wasn't the best metric. In other counties, it worked great. So that was one. Correlation not necessarily equaling causation, right? So just because population goes up and groundwater level goes up, it doesn't mean that they caused each other, and it doesn't mean that the same thing caused either of those. So we're looking at some pretty complex relationships here. And so just because two variables are correlated, we have to think outside of the box maybe for why these things are happening and why these relationships might be occurring. The next is lag and seasonal variation. So it's possible that the withdrawals are having an impact, or something is having an impact, but that impact is just lagged for a while because groundwater systems take some time to recharge, right? So this is a confined aquifer. So if recharge is decreasing for whatever reason, or the withdrawals are increasing for whatever reason, it might take us a little bit longer to figure that out. It's not like there's an immediate, perfect, equal effect. And then last is county boundaries versus nature. So this is something that maybe all of us might come up against in our research, and that is the data is available on a county scale, but groundwater is not limited by counties. Groundwater doesn't care about county boundaries. So there might be a well in Anne Arundel that has these huge drops and we have no idea why. Turns out there's a well in the county right next to it that's withdrawing a ton, right? So we have to consider that maybe there's withdrawals from one well can affect withdrawals from another. So also another analysis I did, I tried to find if the predicted groundwater levels were significantly different versus under the moderate versus the high emission scenarios. The reason why I wanted to do this is, again, temperature is the only variable that we changed to get these predictions. So I wanted to see how big of an effect the temperature changing would have. So it doesn't mean, you know, for these counties where it says no, first of all, 6 were, but the 2 that weren't, it doesn't mean that climate isn't affecting these counties. It just means the groundwater levels, when I made it, you know, an even higher emission scenario versus the moderate, they didn't change much between those 2. And some of the reasons why we think this might be, the aquifer tends to be relatively thick in these regions, so Anne Arundel and Calvert, and we know that relatively thick transmissive aquifers tend to be able to hold on to that groundwater a little better. So it's possible that that might act as a buffer against some of the climate impacts that we might ordinarily see. The other is precipitation patterns. So actually, there is also a recharge zone in Anne Arundel County. So it's possible that these aquifers are getting recharged by the precipitation, and they're having an easier time doing it because they're closer to the recharge zone. So this is actually the precipitation trends from Maryland State Climatologist Office. And you can see right where Anne Arundel and Calvert are, there is a ton of precipitation compared to some of our other areas. So some conclusions for objective 2. 4 out of the 8 counties showed decreased groundwater levels into the future. Temperature was pretty important in the majority of those counties. Some artificial neural networks predicted the counties to have increased future groundwater levels, and that's likely due to the data that was available and, you know, some of the uncertainty of the future projections. 3 out of the 4 counties with decreasing groundwater levels had the temperature variables contributing most to model predictions, and 6 out of the 8 counties were significantly different in groundwater level between moderate and high emission scenarios. So let's get into the conclusions and future management. So how would this help future management, right? So ideally, we want to pair our understanding of these future groundwater levels with withdrawals in order to recommend water resource planning strategies. So let's give an example. So for Calvert County, maximum decreases up to 2050 are estimated by my model to be, you know, the max 3.9 feet of a decrease. So we want to figure out why. So let's do an investigation. So I looked at the Calvert feature importances, and Calvert was one of those counties where the moderate and the high emission scenario weren't significantly different from each other. So I looked at these and I thought, okay, you might be important, but let's look at population, right? So Calvert is the second most populated county within our study area, I believe. And it also has, I took a look at the withdrawals, for example, from 2000 to 2022, and all these withdrawals, government run water supply, institutional drinking sanitary, nuclear power generation, and private water supply, again, withdrawals in gallons per year and the years, these are all kind of population-driven withdrawals, right? So I thought, okay, this kind of looks like a county where population is driving the withdrawals over maybe climate. So I looked at the projected population and I thought, oh my gosh, okay, so there's actually expected to be from now and up until about 2050, about 5% increase in population. So like I said, this is an example where we could say, it sounds like population is likely the greatest stressor on groundwater in this county. So maybe these are some ways that we could adjust. Maybe these need to be outsourced to a different aquifer, or we just need to, rearrange or reprioritize. I mean, it looks like some of these are decreasing already anyway, but anyway, this is how we kind of can investigate using what we know. So this is now an example of Caroline County where climate might drive the withdrawals more. So there's the Caroline projections, and we looked into the withdrawals and we found that the only real use type withdrawing from the Aquia Aquifer is institutional drinking and sanitary, and that number or that withdrawal amount is actually decreasing, right? So what could be causing this groundwater level decline? Well, we looked at the feature importance. We saw T-min and T-av were contributing greatly to the predictability of the model, and they were pretty well correlated as well with groundwater level. So I could say, okay, it looks like temperature is playing a pretty big role in this county. Climate will play a pretty big role in this county in the future, in contrast to maybe Calvert, where population played a bigger role. So I also looked at the population just to make sure, and as expected, it wasn't really increasing as much as it was in Calvert County. So some overall conclusions, irrigated area in acres and population most strongly contributed to the prediction of groundwater levels across all county models. The county models, like the actual artificial neural networks, were able to predict groundwater level pretty accurately. So we had, I think 3 of our models had R squareds of 0.99, and then the lowest R squared was only about 0.82. So pretty great range of predictions. Same thing with the root mean square errors generally being low. Majority of groundwater levels were significantly different between climate scenarios, and the future predictions, as we just saw, can help us plan and come up with some management strategies. So with that, I would like to acknowledge my lab group, especially my advisors. Dr. Azar and Dr. Sharmamati, and then I'd also like to acknowledge the University of Maryland Agricultural Experiment Station for funding my research, as well as all my friends that suffered through thesis writing with me and everything, so I really appreciate them. And now I can take some questions. Thank you. Yes.
How did you decide how much, like what portion of your data to use for training versus testing and validation?
Yeah, so a 30-70 split is pretty common among people who do neural networks. So 70 being training and 30 being testing, because you want your data, you want it to have a lot of data to learn from, right? So majority goes toward testing, training usually. And then the testing, you try to give it a good amount, but you don't want to give it, you don't want it to overfit either. So you try to kind of balance that. And it seems like 70-30 is a pretty common split. Usually people don't go 50-50. So it's basically just from the literature. Yeah, thank you.
Yeah, you just mentioned overfitting. Your R squared values are really high. How did you avoid that in your modeling?
Yeah, so avoiding overfitting in modeling is really challenging. Something I did was using that validation set when I was coming up with parameters for my model. So I used a technique called k-fold cross validation, where, so k-fold meaning however many number of folds. So if it was 3, for example, like 3-fold cross validation, splits it up into 3 parts. It picks one to use for testing, and it uses the other 2 for training. And then it comes up with a score. And then it does that again, picks different ones, comes up with the scores and compares the scores, and then it tells you, you know, what the best parameters are, basically based on different sets of data. So you get to try it on a variety of data, which overfitting is when, you know, you're seeing one thing over and over and over again. So the idea with that is to kind of mix it up to try to confuse the model a little. Thank you. Yes.
Yeah. 2 questions, please. So you mentioned about urbanization in Calvert County. At our Earth Day event, we heard about Charles County,
Yeah.
another place that's really growing. So what changes are happening with urbanization in terms of wastewater? Is the fate of wastewater in terms of recharge?
Mm-hmm. Yeah, so I didn't look too much into wastewater, but I know that actually we have our postdoc is working a lot with wastewater systems and trying to figure out how to use that, reuse that. So I know especially in Calvert County, Charles County, there's been a lot of urbanization in that region specifically. But did you have a more specific question you wanted me to answer?
Well, the other question was going to be related, which is in terms of land use changes like this, what kind of travel times are we talking about between the surface and the Aquia? In other words, if you make some change up here, how long does it take to be reflected in groundwater levels in the Aquia? Right.
So the Aquia is a relatively deep aquifer. So I would say probably looking at, you know, some significant amount of time for those changes to be noticed. The superficial aquifer has a lot of very clear ups and downs because people in the region tend to use that aquifer a lot for irrigation. People also use the Aquia, so not to neglect the Aquia, but I think it would probably, you know, it could take a significant amount of time. But it depends on how thick the aquifer is in that region and a lot of other things, including, you know, the soils vary across the region too. So I think it's kind of hard to generalize for the whole region, but I would say it takes a while to see those changes. Like some of these studies, they came out in, you know, they came out in 2002 and we're still seeing the effects now. So it's, you know, and even though people remediated the Anne Arundel one and they actually saw a stop in declines, it just evened out. It didn't actually improve, like go up, like the groundwater level. So it's possible that, you know, if people stop, which people have been kind of moving from this aquifer to other aquifers, such as the Patuxent, or Potomac, I think, the group, Potomac group, but you could basically see that there's a lag, a big significant lag in the effects. Yeah, thank you. Yeah.
Thank you. First of all, this is so much information condensed into a big seminar, so
Thank you.
appreciate that. I have questions about like this future application. Could maybe somebody using this going forward be able to determine the quality of the groundwater instead of just the quantity? Like, you know, how good is this groundwater? Is it, you know, I don't know if agriculture is kind of leaking into it or having, you know, issues there.
Yeah, so I don't think you would be able to use my model for that, but you could probably use a model moving like forward that does that. So there's actually issues with arsenic contamination in this aquifer as well. So I know there have been some interest in creating this same method, but maybe using it to look at ranges of arsenic concentration or saltwater intrusion. So you could probably use this method. You just wouldn't be able to use my exact thing. But if you had better future data, for example, about irrigated area and acres and population, you could most certainly throw that into my model and get a prediction.
Cool.
Yeah, thank you.
So in St. Mary's County, T-min
Yeah.
the most important,
Mm-hmm.
and to me it's like hotter temperatures lead to more groundwater withdrawal, so why is the minimum temperature more important than the max?
Right. Okay. So T-min, I know St. Mary's has some ag going on, so minimum temperature. So this might actually affect when withdrawals are happening for agriculture in this county. So a lot of people look at minimum temperature to kind of decide, okay, this is when I'm going to start, you know, doing my withdrawals for crop irrigation. So it's possible that this was a really sensitive feature because there's a lot of ties with the withdrawals there. Yeah. Thank you. Okay, any others? Yes.
So in Caroline County, the groundwater level went down until
Oh, that was,
Thick.
wait, let's go through. I think maybe you mean
Calvert, right?
Calvert, yeah.
So was it population was going up and then leveled off and then
Yeah.
and maybe,
Yeah.
or is that sort of what you think happened?
That was one of my hypotheses for this, was that when you looked at the variables, and also I think, again, the irrigated area in acres variable might have thrown this as well. Because once you start predicting irrigated area in acres all the way out to 2090, it's probably not the most accurate prediction in the world. So it's possible that, yeah, like those variables evened out after a certain point, and then the groundwater level responded by going back up. So I definitely think population and the irrigated area in acres variable were responsible for this. Yeah.
So even if population is not as important in your bars as
Yeah.
mid,
Yeah.
it could still be important, like,
Yeah.
what kind of importance you need in terms of explanatory power?
Yeah, so like the feature importance is kind of how we figure out what the model is thinking. So it doesn't necessarily mean, oh, I know 100% for certain that this is the most important variable in the actual system, like I was in there and I did all the measurements. No, but it just gives us an idea of why the predictions are what they are. So when I see a high, for Calvert, when I see, high population, I go and I can map out the population, and the population does even out after a bit. So this is probably what's causing that change. Is it, is that change exactly perfectly what we're going to see in the future? I don't know, but yeah, I can tell you what's causing it. Yeah.
That's interesting, thank you.
Yeah, thanks. Yes.
This is like kind of, okay, I'm curious. Is there a way to like quantify uncertainty in terms of the predictions?
Yeah. So basically that's kind of what I was trying to do with the root mean square error estimate. So trying to figure out how different my predictions are from the actual estimates. Like if they're significantly different, then that would mean that there was a lot of uncertainty in the estimates. And then the validation is also another way to kind of reduce the uncertainty by training on a wide variety of data. Yeah, I know there are other metrics for evaluating these models. Like a lot of people use, I think Nash-Sutcliffe for these. So there's like different ways of figuring out how much like uncertainty or error there is. But I don't know for sure like the perfect term, but I definitely think the R squared and the root mean square error and mean squared error address that. Yeah. And then you can also look at like, yeah, I mean, because the R square is basically showing how much of the variance in the groundwater level is described by like the model. So yeah. Okay. Yes. Sorry.
I'm having a hard time getting my head around all of this.
Yes. Let's talk.
Well, so from the beginning, in my mind, precipitation has to be there.
It totally, yeah.
And so
Yeah.
an aquifer is recharged because water comes from somewhere and goes into it.
Totally. Mhm.
And so there's a spatial disconnect. I mean, why isn't precipitation important?
Yeah.
Just
So
help me here.
I think, well, it is. I think it is. It's just that I think it would be important if it was lagged. So my variables are just as it is compared to the groundwater level, right? But we know that recharge takes a long time. We also know that not necessarily all of precipitation becomes recharge. So there's probably some more intricate relationships that have to be modeled there for us to see such a strong connection. Okay, sorry, you had your hand up for a while.
Oh.
I
was just, you have like a.
Yeah, but
The follow-up question was,
Okay.
would it be easy to lag precipitation?
Yeah.
in the modeling?
Yeah, so there's actually a lot of models that do this like in other regions, and they just kick it back by like a month or two, and then they can basically simulate that. But those were doing it like not for years and years and years, which is kind of where my project is unique. Those were trying to predict like a month ahead. So they were just shifting everything back a little bit and then giving it to the model that way. So it would be very feasible to do that. It's just that, I didn't do that. I didn't get a chance to do that yet, but it would be a great future thing to do. Yeah. So precipitation is important. It's just the effects of precipitation in terms of the correlations and everything, just the connection wasn't really there. And if the correlation wasn't high, I was worried it was going to add extra noise to the model and make the predictions worse. So yeah, thank you. Okay.
I was wondering when you think you can come back and check the data and be like, was I right? You know, like, are you keeping up with the groundwater data to see?
Yeah, I mean, what, you mean like in the future? Like,
yeah, like maybe not like, of course, 2100, but.
You don't think I'm gonna make it that long? No kidding.
Go for it.
But yeah, so I guess the predictions are actually monthly, even though I aggregated them to a yearly average. So
Right.
I could probably check like, yeah, that's a great idea. I could probably check next month and see.
Give us an update.
Yeah, and update you. That would have been pretty cool to do. Yeah, thank you. That was a really cool insight. Yeah. And then, of course, I have to make sure I have to figure out what climate scenario we're in. That's the other thing. Yeah, okay, yeah.
Sorry, I came in late and may have missed this, but for your model development, did you always keep the variables in the model, or did you pull variables out to improve the
Yeah, so that was part of the model development. Like we were running with actually evapotranspiration in the beginning.
Okay.
And then we thought, future evapotranspiration estimates sounds like something that might be difficult to do, or something that might take some significant doctoral level effort to do. So we actually ended up taking that out of the model, but I actually had to go retrain in the models to work better for that data. So the model started out one way, had to readjust after I removed some. And they actually advise, like when I say they, the people that make models advise that you kind of limit your parameters. You don't want to have like 7 or 8 or 10, because then it just starts getting out of hand. You can't really tell what's causing what.
So there wasn't like a statistical threshold where you pull variables out of the model?
Right, no, so I tried to train all of them as best as I could to get the highest R squared that I could, and I believe I was pretty successful. And pulling things out were pulled out because, yeah, I mean, there wasn't a statistical reason, but the reason would be, okay, you know, projecting this into the future would affect the model's performance significantly. So I decided to just go and remove it, because what's the point of having a model that perfectly predicts groundwater level that already happened? So we need the future component. So if the future data is there, and I know it is, you know, there's ways to approximate evapotranspiration, then it would definitely be feasible to add them back in. Just retrain and retest.
So I have a question. If you go to slide number 8.
Yeah, let's go.
So you mentioned this this concept of a black box, like this hidden layer.
Yeah.
Lots of layers potentially.
The secret layers.
Yeah. Is this black box also termed the latent space or a latency space? Does that make sense?
That's ringing bells.
Okay, so I was talking to a colleague recently about this, and he was all excited about some new techniques, and I don't know if you're aware of it. Like, I just wanted to ask generally about this. Like, there are, I guess, techniques available now where you can, I don't know if you can do it based on the way you ran your model and everything.
Yeah.
There are ways to explore that space.
Yeah.
And to retrieve information about your output layer, for example.
Right.
And so I don't know if you have the ability to do that here, but whether you do or if you could do it differently so that you could, what information do you think you could get from that? Because going back to Lance's question about precipitation seeming to be important,
Yeah.
even considering these lags and everything, maybe precipitation really does have an importance,
Yeah.
irrespective of the lag.
Right.
But it's just so interconnected with everything
Yes.
else that it washes out of your
Exactly.
So, but maybe you could go back with some tools.
Kind of tease it out. Yeah. So there are a lot of ways to kind of get a peek into what's going on. One of them I actually tried to do. I printed out but the thing is, you have to realize with my neural networks, I have like 3 hidden layers, which is what I modeled here. but some of the neurons, I mean, I have like 50, 40, 100 going on, like in terms of the layers. So I actually went in and tried to print out like every weight and every bias that was affecting everything. And I know obviously the activation function I use, which is rectified linear unit function, if anybody's curious, to influence the predictions or to introduce nonlinearity. And I know there are definitely other ways that you can kind of figure out, you know, again, like by printing out the weights and doing an analysis that way. And I would definitely be interested in doing that in the future. I think it's super cool that there's, you know, more ways that we're learning to kind of figure out how things influence each other. And I actually did one thing that I did do, which I just slid in at the very end. This was one thing that I was like, just to look at my model a little bit more, I actually made a kernel density plot. This is a little hard to explain, but it's basically how different my values are, like based on like training, testing, and observed versus predicted, because I was seeing those train and test plots that I showed you earlier, and I said, these are looking really similar, and I got scared that I was using the same set. And so I actually went and plotted this density, which is basically how often a certain value occurs within the series. So like, you know, it's looking like 130 is appearing a lot. Sorry, this is, oh my gosh, this is even smaller for you guys. I'm so sorry. Okay. So, sorry, yeah, so this is an idea of basically getting an idea of how your data itself looks, which is another way to get insight, which is really cool too. You can kind of dissect your data a million different ways and say, these models are going to do better at predicting values within this range because this range is overrepresented in the data set, right? So that's also something cool too to look into. Yeah, there's so much to learn. Yeah, thank you. Okay. Oh,
Where does this neural network live? Like, where do you run it on?
yeah, so
Do you buy it or do you?
this little tiny MacBook has run 8 artificial neural networks. No, so I did not know how to code when I came into this project, and I took this class that basically helped me figure some of the basics out, and we did all the coding on Google Colab. So I've just been coding neural networks on Google Colab and Python, and it's been working great. So that's what I've been doing, and that's where it all lives. And the best part about it, and also the best part is like I could just share it. Like if somebody was like, "Oh, I want to see your code," I just add you to the little file, and you can go see everything. And I'm working on getting like a GitHub profile so I can kind of post that out into the world so people know how to do this. And I'm making sure it's in my thesis, so if another graduate student comes along and wants to build a neural network, they actually have a little path. Yeah, trying to help out future me, or past me. Yeah, but yeah, really good question. Yes.
I have a question about the literature, kind of like what Melissa was saying before. Have you seen papers that are probably a couple decades older that have done something like prediction for groundwater and then have done another paper, maybe like comparing and how they would like, how to improve, so maybe like models in the future could learn from things they missed,
Yeah.
and that they know what actually happened?
Yeah.
Is that a thing?
Yeah, that's a thing. So there's actually been a lot of like papers. They're not really in this region. They tend to be in like very intensely water stressed regions. So actually there's a ton of papers on this from like Iran and stuff, like on, or at least like set in Iran. And there's also there's one specifically that I'm thinking of where they did it, and they literally just did like they did it weekly, and they tried to just predict like a week ahead or something, like really small scale. And the correlation idea, where I got the Pearson's correlation coefficient idea, is from the past literature. So these people were like, hey, we ran this analysis to figure out what variables to put in, and it worked really well, so you should just try that. And the rectified linear unit function, which is the activation function I use, which is the thing that the neurons get, and then it basically decides if the neurons are getting activated and passing on the signal to the output thing. That was also informed by literature. So I went and I thought, okay, what function is gonna perform the best. And literature has found that is a very popular function for a reason. It's very good. So there are a couple other functions like people use, like sigmoid function, linear function, but I didn't want to use linear because I wanted that non-linearity. So yeah, there's a lot of people that have done this stuff before. They've used different approaches. Some of it isn't all completely applicable. Like some people were using surface water they were predicting surface water levels. So they were using surface water measurements, and precipitation had a really big effect there. So yeah, there's a huge wealth of literature on this. There's nothing like this, to my knowledge, predicting into the future the way I did in Maryland. There were the people that did the agricultural study, which was really cool, where they looked at the agricultural areas and found out the groundwater level changes. That was something that I took a lot from. Yeah.
I just want to say thank you, Jen. I mean, that's really great.
We're
you gave. One thing is in 2007, there is a thesis in my office. One of my PhD students used the soil moisture satellite images of surface soil moisture to predict the uncompliant water table fluctuations in Maryland and ground truths with the actual wells in several locations in Maryland. If you're interested, you're most welcome to borrow.
Yeah.
And so I think I'm gonna stop it there and say, just give Jen a round.
Thank you.